We are live. So good morning, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, which we do have a few classes today, we are all about bringing conservation, adventure, and science into classrooms around the world. And we're really excited because this whole month of October has been celebrating space. We've done sessions with astronauts, astronomers, engineers, technicians, and more from across the world of space in the US, Canada, and more. And so it's been a really fantastic celebration, and thank you guys for being a part of that. We've got 4 classes joining us from across North America right now, so I'm going to go to each and give them a chance to say hi. We've got Miss Coyle's grade 6s in Edmonton, Alberta, not Ontario. It's not where Edmonton is. Hi, guys. Awesome. We've got Miss Sharp's grade 12s in Parma in Michigan. Hi, guys. Oh, your mic isn't demuting today, but hi and welcome. And see, there is tech difficulty, Sarah. I told you. We've got Mr. Taylor's grade 9s in Niagara Falls in Ontario. Hi, guys. Hey. And last but not least, joining us for the very first time, we've got Miss Powell's grade 9s in Toronto, Ontario. Hi, guys. Oh, everyone's mics didn't work today. There we go. Hi. Perfect. All right, so the reason you guys are all here today is for our speaker. So we are joined live in Baltimore, Maryland by Sarah Hörst. So she is a planetary scientist and assistant professor at Johns Hopkins University. And she is fascinated with the chemistry of other worlds in our solar system, understanding those amazing molecules on the surface, and maybe if there might be the potential for life somewhere along the line. So I'm gonna turn it over to her to blow our mind with all the cool stuff she gets to do. And so without further ado, thank you so much for joining us, Sarah, and take it away. Oh. There we go. You should be good. Yes.
Good morning, everyone. Are you good? Can you hear me? Yes?
Yeah.
Good? Oh gosh, now I'm awfully big. Okay. Good morning, everyone. I'm actually at home. I have a new puppy, and so I'm trying to make sure that he hasn't gone rogue anywhere at the moment. He might come visit at some point. We'll see. Thank you so much for having me. I'm a planetary scientist at Johns Hopkins, and a lot of people actually wonder what a planetary scientist is or how one gets to do that. So I just wanted to tell you quickly what that is before I tell you anything else. My college degree is actually in planetary science, which is a pretty rare thing. But all that means is that I had to take all kinds of classes, both when I was in college and then when I went to graduate school, in all different sciences. So I took geology classes, I took physics classes, I took chemistry, I took math, I took some biology classes, I took astronomy classes, and that's actually one of my favorite things about being a planetary scientist is that we get to do all different kinds of science, so I never got forced to pick one. And so that's just a little bit about what I do. I'm going to attempt to share my screen, which always ends badly, but maybe it will work.
Have faith.
Let's see. Oh, it might actually work for, let's see. Maybe it'll work. Come on, you can do it. Did that work?
Yeah, we've got your main slide in the middle now and your slide deck on the left. So if you go to presenter mode, there you go.
Is it? Okay, awesome.
You're perfect.
Well, the last time I did this, it refused to actually go into presenter's mode, and so I just had to do it from the slides, which was fine. It always works. So I want to tell you a little bit today about the best place in the solar system, which is Titan, which is awesome, as you can all hopefully read on this slide. So Titan is the largest moon of Saturn, and actually, I don't know if I can, I need to maybe move this for a second. There we go. So this is Saturn. Hopefully you all can recognize that Saturn is the planet with all of the rings. But if you look over to the right a little bit, there's a kind of orangey brown dot that's on the bigger side, and that's Titan. So Titan is the largest moon of Saturn. It's actually the second largest moon in our solar system, which I think is the next slide. Oh, now it doesn't want to advance. That's cute. Okay, hold please. There we go. So this is a really cool compilation of what Emily Lochtewalla at the Planetary Society has called the not planets. So these are places in our solar system that we have visited with spacecraft, that we've been able to study with telescopes, that are not planets. Titan is the one in the middle. The biggest moon in our solar system is Ganymede, which is the just a little bit above it. which is the largest moon of Jupiter. And they're about the same size. But the reason that I like to show this graphic is because it shows why Titan is awesome. And the main reason why so many of us are interested in trying to study Titan. And the reason for that is if you look at all of these pictures of all of the not planets, you can see their surfaces on all of them. And so you can see that they have craters. In the case of Io, which kind of looks like a piece of pizza, you see that it has volcanoes everywhere. But when you look at the picture of Titan, you can't see the surface. And the reason for that is that Titan has a really thick atmosphere. And it turns out that Titan is the only moon in our solar system that has an atmosphere. And so immediately that tells us that there's something really weird and something really interesting going on about Titan. And the other thing that is really weird and interesting about Titan, before we know anything else, is that Titan is the only other atmosphere in our solar system besides the atmosphere of Earth that is dominated by molecular nitrogen. So Earth's atmosphere has kind of two main gases, molecular nitrogen and oxygen, the oxygen that we breathe. Titan has two main gases, nitrogen like Earth, but then instead of oxygen, Titan has methane. And so that's really interesting to us because all of the other atmospheres in our solar system, Venus, Mars, those are both CO2, Saturn and Jupiter have hydrogen atmospheres. So all of these other atmospheres are different. And so we have a lot of questions about where Earth's atmosphere came from, what that means for how life originated on Earth, what kinds of chemistry was happening when life was trying to get started. And we can't time travel. We can't go back in time to that period of Earth's history when those things were happening, but we can build spacecraft and send them to Titan and try to study processes that we think are really similar that are happening in Titan's atmosphere right now, today, as we speak. And so that's one of the reasons why Titan is so interesting to us. Let's see if I can get the slides to advance this time. I already said most of these things. The one thing that I wanted to mention is that Titan is very, very cold. I always mean to update this slide because people don't necessarily think in Kelvin. The surface temperature on Titan is 94 Kelvin, but it actually doesn't matter if I tell you what that is in Fahrenheit or Celsius because it's so cold, you'll have absolutely no sense of what that would mean if you found yourself trying to step outside on Titan. One of the main things that it means is that there is no liquid water on the surface of Titan. Titan's crust is made out of water ice. And at that temperature, water ice is the way that rock is on Earth because it's so cold. Let's see what the next slide is. So we have studied Titan in a lot of different ways. So the Voyager spacecraft were our first really good look at Titan, and they flew through the Saturn system actually before I was even born. So definitely way before all of you were born. So this is in the early 1980s. And then after that, we sent this really incredible spacecraft called Cassini-Huygens, which was in orbit around Saturn from 2004 until 2017. Which is really incredible. So this is a picture of the spacecraft. It was a joint mission between NASA, the US Space Agency, and ESA, which is the European Space Agency. Let's see, I already said. So it launched in 1997. It took 7 years to get to Saturn. So you can imagine how patient everybody had to be able to wait for it to get there. Cassini is the orbiter that was in orbit around Saturn. And Huygens was a probe that descended to the surface of Titan in 2005. And you can see the probe in this picture is the kind of big gold circle. And that's the heat shield for the probe that protected it while it was entering Titan's atmosphere. And one thing just to notice about this picture is that all of those kind of white human-shaped creatures at the bottom of the picture are people in bunny suits that were helping assemble the spacecraft. So Cassini wasn't like, the kind of cute little car-sized Mars rovers. Cassini was about the size of a school bus. And Cassini carried 12 different instruments, some of which were to study Saturn and the rings and the moons by looking at them. We call that remote sensing. And so they look at the way that light from the sun interacts with the surfaces or with the atmospheres. And some of them were what we call in situ, which means that they will actually directly sample some of the material and do things that are kind of equivalent to smelling or tasting or touching. And so the spacecraft had a mix of those kinds of instruments. The Huygens probe had 6 instruments, and similarly, they were a mix of ones that just looked and ones that kind of tasted or smelled. We purposefully crashed Cassini into Saturn in September of 2017. The reason for that, there were actually 2 reasons for that. So one reason was that we could actually do science on Saturn while we were doing that. So we hadn't gotten to actually use any of those instruments that were for smelling or tasting on Saturn yet, because if we got close enough to do that, then we were going to crash into Saturn, and we weren't ready to do that yet. But once we were ready to do that, we were able to find out a lot about Saturn by crashing Cassini into it. The other reason, though, is that we think that some of the moons of Saturn might have the possibility of having life. So not just Titan, which is really cool, and I'm going to tell you a little bit more about in a few minutes, but also a moon called Enceladus, which I think actually I don't have a picture of in the slide deck, which is frustrating. But both Titan and Enceladus have subsurface oceans. So they have liquid water oceans beneath the crust of the moon. And we think that that's a place that life that could have been carried on the spacecraft could live. And so we have to be really, really careful not to accidentally bring little microbes or something from Earth and then have them end up in liquid water on another planet. And so the best way to make sure that that didn't happen was to crash Cassini into Saturn to protect the rest of its moons from getting contaminated by things that might have hitched a ride from Earth. And so that was why we did that. Let's see. Okay, that's another picture of Titan. And one of the reasons why I like to show this picture is because I said that you can't see through the atmosphere, and that's not entirely true. So the cameras were designed with everything that we learned from Voyager so that they could look in really, really, really specific regions of sunlight where the sunlight does get down to the surface. And so we can see in those little teeny tiny specific regions. And so here you're seeing partially the atmosphere. That's why it looks so fuzzy. In fact, that kind of white wispy thing towards the top of the picture is a giant cloud that's made out of methane. But you can also see down to the surface. So if you look at the top of the image, which is the North Pole, you're actually seeing a bunch of lakes and seas, and I'll show you much better pictures of those in a second. If you remember, I said that water can't be liquid on the surface, and so those aren't lakes and seas made out of water. They're lakes and seas made out of liquid methane and also a molecule called ethane. The ethane is made from chemistry that happens in the atmosphere that's driven by sunlight. And there's a lot of other molecules that are made by that chemistry too. So the molecule propane, like you use in your grill at home, is also made by chemistry in the atmosphere, and a whole bunch of other molecules that contain carbon. And some of those will end up in the lakes and seas too because they're liquid at Titan surface temperatures. The other dark material in this picture, which is further down towards the middle and towards the bottom, are actually big dune fields. So Titan has extensive sand dunes. They actually cover from basically the mid-latitudes at the southern hemisphere all the way to the mid-latitudes of the northern hemisphere, and they wrap all the way around the moon. So even though you can only see half of Titan in this picture, if we were to look at the other side, you would also see sand dunes on that side. And I'll show you some more pictures of those in 1 second. When we landed the Huygens probe on the surface, we had never seen really the surface before because Voyager couldn't see through Titan's atmosphere, and Cassini had only really just gotten to Saturn. And so people were betting what the Huygens probe was going to land on because we didn't know what the surface was made out of. And some people kind of guessed like the safe things. It's going to land on ice because we were pretty sure most of the surface was made of ice. Some people thought it was going to land on tar, so kind of this like goopy carbon stuff that gets made by chemistry in the atmosphere. Interestingly, only one person said liquid, which was fascinating because at the time we thought maybe a good chunk of the surface was actually covered in lakes and seas. A couple of people just said, I don't know, we're not going to be able to figure it out. 2 people very pessimistically said that it was going to be dead on arrival. And then one person, and this is by far my favorite answer in this betting pool, very optimistically suggested that it would get eaten, which would have been amazing. I can tell you right now that the Huygens probe did not get eaten, at least not while we were getting any data back from it. I know we were all very sad about that. But I always just like to show this picture because this is from 2004. And so we were still, we were still kind of at the beginning of learning about Titan, to the point that we didn't actually really even know what the Huygens probe was going to land on when we sent it to the surface. And it's really exciting because we now know so much more about Titan. And I'll show you more of that right now. So these are some of the images that the Huygens probe took while it was descending through Titan's atmosphere. So the one kind of inset image at the top shows that there are a bunch of rivers and streams that were flowing down this kind of hilly area into the area where the probe actually landed. And again, just to remind you that we know that it rains on Titan. I showed you the pictures of those clouds. We know that we have lakes and seas, but that rain is methane and ethane. It's not water. And then you can see at the bottom right that there's the picture that was taken from the surface. And the thing that's really cool about that picture is that those kind of rocks look like things you might see in a stream bed on Earth. And so they've been rounded by erosional processes over time. And so that's really exciting. It was actually the first time we'd ever seen that on another planet. We've now seen that type of evidence on Mars as well, but we found it on Titan first. But the thing that's really cool is that there isn't anything that we think of as rock on the surface of Titan. So all of the material that we think of as rock has gone to the inside of Titan where its core is. And so we think that those pebbles that we see in that picture are actually made out of water ice. Or maybe a mixture of water ice and some of that carbon stuff that we found coming out of the atmosphere. And so Titan is interesting because it has all of these processes that are very Earth-like. So we see these lakes and streams, we see pebbles, we see sand dunes, we see all of these things that are very, very similar to Earth. But then when we look at the materials that they're made out of, they're really different. And so it's been really important for us trying to understand how planets work, because this is a really good test of our ideas about how streams work or how sand dunes work, is to have them happening on a different planet that has different gravity and has different materials where these processes are happening. Let's see what the next, oh, that's just that picture again showing the stream channels. This is that same picture now has been kind of false colored to give you an idea of what it might look like on the surface. And then for scale next to it is a picture from the moon with an astronaut boot print to give you a sense of how big those cobbles are, because it's hard to tell when you just look from the camera. So I mentioned that we have all those lakes and seas at the North Pole, and we use a different kind of instrument to be able to study the surface really well. So this is a radar instrument which can see through all of the stuff in the atmosphere. So it gives us a really good idea of what the surface looks like. And these are some of those lakes and seas that we see on the surface of Titan. There's also all of these river channels that you can see. So this looks very similar to Earth. One of the things that's really cool, and actually I think this is one of my favorite pictures that was taken from Cassini. So some of you may recognize this if you've ever flown over a river or a lake that was pretty smooth, and you could see the sun actually reflect off of that liquid, and we call that a sun glint. And this is actually a sun glint off of a lake at Titan's North Pole. We'd never seen a sun glint off of a extraterrestrial body of liquid before, because Titan is the only other place that right now has liquid on its surface. And so that was really cool. And it was neat because we didn't, at the time, we didn't know which lake it was coming off of, but people went through and they reconstructed exactly how the spacecraft was oriented and eventually figured out exactly which lake it was reflecting off of. And it turned out that that lake didn't have a name yet. And we name all of the lakes on Titan after lakes on Earth. And so there's a Lake Ontario and, you know, all the lakes that you hear about on Earth. And so the scientists decided to name this lake Jingpo Lacus, which means mirror lake, because of the mirror-like reflection that we got to see. So that was really cool. This is my favorite Titan picture. this is again just showing Titan's atmosphere, and it was really cool because when the South Pole went into winter, all of a sudden this giant cloud formed. So you can see that it looks like Titan kind of has like a belly button in this picture, or maybe it looks like a basketball where there's like the thing where you inflate it at the bottom. And so it turns out that that was a giant vortex that formed at Titan's South Pole. And we can actually look at it now looking down from above. This is hydrogen cyanide ice, which is an extremely toxic compound. So Titan's not a great place to just go hang out without taking a lot of precautions. And we know that it's a vortex because we actually have images. Hopefully this will work. There we go. We have images of it over time, and so we can see that it was rotating. And so a lot of people are still trying to figure out exactly why this happened, but it tells us a lot about how Titan changes with seasons. And it has seasons just like Earth. It's tilted almost exactly the same amount on its axis as Earth is, Earth years. And so the seasons are a lot long, which is really bad news if you don't like winter, for example, because winter is much longer on Titan. There we go. So that was just like the world's quickest tour of why Titan is really cool. But I wanted to tell you for just a minute about what's next for Titan, because we're super, super excited that there is a next for Titan. So I mentioned that when we sent the Huygens probe to Titan, we didn't even know what the surface was made out of. Well, it turns out that we still have a lot of questions about what the surface is made out of that are keeping us from being able to understand a lot of things about Titan. But in particular, one of the things that we really want to understand is the chemistry that's happening in the atmosphere makes all of these really complicated molecules that end up on Titan's surface. And that's kind of my main area of expertise. And we think that some of those molecules are the kinds of molecules that might be important for the origin of life. That doesn't necessarily mean that we think there might be life on Titan, although we're certainly going to try to check. But we want to try to understand how these processes happen, what that means, again, for the possibility of life originating on Earth from this type of chemistry, and also what that means for where there might also be life somewhere else in the solar system or in the universe. And so now that we know a little bit about the surface, and we also know that we want to know more, about 3 years ago, we started working on a mission proposal at the time for a spacecraft called Dragonfly. So Dragonfly is a dual quadcopter. Some people would also call it a drone. And so our idea was basically to send this mobile platform. So a spacecraft that's kind of like the Mars rovers in the kinds of science it can do. It has 2 drills, it can sample the surface, it can put them into instruments and measure the composition directly. It has lots of cameras, and so we can study the area around where we're going. But instead of driving to get to our next spot, the way the Mars rovers do, we're going to fly instead. And the reason for that is that Titan's gravity is about 1/7 of gravity on Earth. And Titan's atmosphere is 4 times as dense as it is on Earth. So if you personally went to Titan and strapped wings onto your arms, you could flap your wings and fly under your own power. It's that easy to fly on Titan. And so we thought we should take advantage of that and send a flying spacecraft instead. And so this past June, NASA said, okay, so apparently we're going to do this now, which is really exciting. So if this works, which it doesn't always, I can show you a little bit. Oh, come on. There we go. Just show you a little bit about, media not found, failure. Okay. Well, we were bound to have some kind of technical difficulty that was going to cause us problems. I know, it always happens. That's so sad. I could attempt on the fly to try to find the video on my computer, but that always ends badly too. But I can describe it. So basically the idea now is that we are going to launch in 2026. It takes us 8 years to get to Titan. So it actually takes us even longer than Cassini took, because Cassini was lucky. They were able to fly by Jupiter. And because Jupiter's so big, it kind of slingshots the spacecraft. And so they were able to get to Saturn faster. But Jupiter's in the wrong part of the solar system for us right now. And so we can't use it to get to Saturn. And so it's going to take us even longer to get to Saturn than it took Cassini. So we arrive at Saturn and the Saturn system at 2034. And when we get to Titan, we'll be all buttoned up in our aeroshell and our heat shield and everything. And then we'll open up a big parachute and descend on parachute until about 1 kilometer above the surface. And then we'll jettison the parachute midair 1 kilometer above the surface and start flying. So we have to use our flight systems to land. So that's going to be a very stressful day in the life of the members of the Dragonfly team. And then we'll fly to our first landing site. Our plan currently is to land in an area near what's called Selk Crater. And so the reason that we're going there is because we're going to land in between some of the dunes that are near Selk. It's very, very flat there. And so we know that will be a safe landing site for us. And so we'll go there first. And then once we land, we can sample the surface, we can measure the composition, we'll take lots and lots of pictures. We have instruments to be able to measure the wind speed and the methane humidity and all of those things. And once we have our instruments all kind of checked out, and we know everything's working right and we're kind of done doing science there, then we'll take off and fly again. So our eventual destination for a mission that lasts 2.5 years is this crater, Selk Crater, that we'll be landing near. And one of the reasons we want to go there is because I mentioned like 5 times already that there's no liquid water on the surface of Titan. But when there are impacts into the surface, there are pools of liquid water that last for about 10,000 years. And so the chemistry in those places is very, very, very different. And so we want to go study one of these places where we knew there was liquid water at some point so that we can understand how that chemistry has happened and see what kind of molecules are there. And so we'll fly about, I forget exactly how far we fly now, but I want to say we fly, it's like on the order of 100 kilometers. Maybe 200 kilometers, I forget exactly what the distance is, to get into the crater. And then if NASA decides that they want to extend our mission, and if everything is still working correctly, then we can keep flying for a long time because we don't have any particular constraints that mean that the mission could only last for 2.5 years. So hopefully we'll last much longer than that. We'll see what NASA has to say about that. And that's all I have in terms of slides. So I would love to take questions that people have.
Awesome. Thank you so much, Dr. Hörst. All right, we've got a few groups watching on YouTube as well. So if you guys want to type in questions in the chat bar, I'll happily pass them along to Sarah. But yeah, let's dive right in. And we'll start with a question from our class here. So Miss Powell's class, if you guys want to kick us off with a question, go for it. Question from Miss Powell's group. Anyone? Nope. We can come back. I'll go to Mr. Taylor's class first then. Come on, guys. Go for it.
Yeah, we were just wondering, in your experience, when you were doing your degrees and stuff, did you do any exploration of different parts of our world which would make you better suited to understand what you're looking for on other planets?
Yeah, so I mentioned that I took some geoscience classes, and one of the things that we often did in those classes was we would go on field trips. And so we went to places like Meteor Crater in Arizona, the Grand Canyon, some other kind of desert areas in Southern California. I don't do a lot of that type of work now, but there's lots of people in planetary science who do. So people who go to Antarctica or to the Arctic, to study different processes involving ices. There's people who go to places like the Atacama Desert in South America because it's very, very dry there. So we think that's a good analog for Mars. And so people definitely do a lot of that type of work, both to try to understand what those places are like, but it's also one of the places that we go to try to test designs for instruments that we put onto spacecraft or to test the spacecraft themselves. So there's a group that is trying to figure out how you would get below the ice on Europa, which is one of the large moons of Jupiter, and then how you would study things below the ice. And so they go to Antarctica and actually, try to send different kind of spacecraft prototypes below the ice and see what that would be like. And the cool thing about that is that we get to learn a lot about Earth too, in the process of doing all of these things to help us better figure out how other planets work.
Very cool. All right, let's go to Miss Quayle's class. And Sarah, if you could unmute, or not unmute your mic, if you could get out a screen share so we can see you again, that would be fantastic.
Well, that's no fun.
Yeah. But yes, we'll go to Miss Quayle's class. Come on up, guys.
Did that.
Hello.
Hey, did anyone have any questions?
Yeah. How long did you study for the Titan? Like how long?
How long have I been studying Titan?
Yeah.
Yeah. That's a really good question. I've actually been studying Titan since I was 19 years old. So I've been studying Titan for almost 20 years. So I started working on it when I was in college, as a project that one of my professors asked me to help with. And that was, what is even weird about that? That was before Cassini got there. So it's been a long time.
Awesome. Great question, guys. Miss Sharp's class had some major technical difficulties, as you predicted. So they ended up on YouTube, and I wanted to pass along their first question, which is, what is the most interesting part of your job, Sarah?
Oh, people ask me that question a lot, and I'm never quite sure how to answer it. I think one of the best things about being a scientist and being a professor is that every single day is different. And most of the time I don't even know what my day is going to be like when I wake up in the morning, which sometimes is a little frustrating, but most of the time it just kind of means that things are an adventure. So sometimes I'm talking to classes like you all, sometimes I'm traveling to meet with people that I do science with, sometimes I'm writing things, sometimes I'm reading things. Sometimes I'm getting to plan to send a dual quadcopter to Titan. So that's, I think, probably the best thing is just that I get to do lots of different things. And for sure, this job is never, ever boring.
Very cool. All right. Miss Powell's class will come back to you guys. It looks like you guys are packing up and heading
Yeah,
for
sorry,
another
we've
class.
got the end of class and they've got to go to their next period. Sorry.
That's okay. Did they have any
Bye.
questions before we go?
Bye. Thank you so much. It's very interesting.
Awesome. Thanks, Miss Powell. All right. We'll go back to Mr. Taylor's class then. Come on up, guys.
Then you want to ask our question? About the time it takes for them to control the Wi-Fi.
We have another
Hey,
for you guys?
Hi, we're wondering, because it's so far away, when I'm trying to fly my son's drone, which I crash all the time, how much of a delay is there from, say, trying to maneuver left or right, up and down, between it actually receiving that and doing what you want it to do?
Yeah, so we won't be flying it. It will be flying itself. So the one-way light time, so the amount of time that it takes just to send a signal to Titan, and then of course it would take that much time to get back to Earth, is about an hour to Saturn. And so Dragonfly will be flying completely autonomously. So basically we'll tell it where we want it to go, and it will figure out how to do that. So some of the most important people on our team full of very important people are the people who are writing our software to make sure that it understands what all of the different possible failures could be, and then has plans for them. And so we won't actually be flying it, which is actually very similar when we drive the Mars rovers. They also have to drive autonomously because of the time delay between Earth and Mars. The other thing, I just had to laugh when you were talking about crashing it, because people have that experience in everyday life of, getting them stuck in trees or, telephone poles or whatever. And, it's become this kind of joke on the team that we're actually fine with that happening. If it crashes into a tree on Titan, we will be super, super excited, because that means we found life elsewhere in the solar system. So we kind of hope that might happen, because that would be a really exciting discovery.
All right. Fingers crossed for rogue Titan trees or something to eat the copter in midair and fulfill that guy's dream. All right. Miss Quayle's class, let's go back to you guys for a second. Hey.
So
my question is, when did you figure out Titan existed?
So we have known about Titan since the 1600s. So actually, if you have this is a ridiculous question to ask, but I can actually see some of the classrooms right now. Have people seen Saturn through a telescope? Anybody? If you
Yeah,
could
put up your
repeat
hand if
it.
you've seen Saturn, guys. Few
Okay.
people, most not, but a few, yeah.
Okay, so if you can see that Saturn is a dot with ears, if you have a telescope where you can see the rings, you can usually see Titan. So it's just a little dot next to the bigger dot with ears, but you don't actually need a very good telescope to be able to see it. And so basically, as soon as somebody built a good enough telescope and pointed it at Saturn, they knew that it had a moon. But we didn't really learn anything else about it until the 1900s. So we've really only been actively studying Saturn, or actively studying Titan for, I would say, probably about 50 years, maybe 60 years. Yeah.
Very cool. And by the way, may I say, so with Miss Coyle's class and with Mr. Taylor's class, you guys are in areas where there's the Royal Astronomical Society of Canada, and so they literally bring telescopes to community events, and you can see Saturn's rings. It's one of the coolest things you'll ever do. Sounds ridiculous, a dot with a line through it, but it's incredible, and I really encourage you to do that. Now, one question we get, Sarah, a lot from class, we haven't got it yet today, is these missions cost a lot of money, and so I'm curious, why go? I mean, you're very excited. Why? What's the end goal? Is there a purpose for this that's really exciting that you want to share with us?
Yeah, I mean, I think there's, we have a couple of different goals, but I think, kind of the biggest picture goal for us is really just related to trying to understand how life originated on Earth, and what the conditions for life are, both in the solar system and also outside of the solar system. So one of the things that's really cool about space missions, and about space science in general, is that everything we learn about one place or one part of space is important for understanding all of the rest of it, because what we're trying to figure out is how planets work, and how planetary systems work and all of these things. And so the more we learn about Titan, the better we understand Earth. The more we learn about Mars, the better we understand Jupiter. Sometimes it's hard to kind of understand the connections, but that's really what we're trying to do. And that will help us answer these really big questions that we have about whether there's life elsewhere in the universe, and how life started on Earth.
Outstanding. And of course, we get to explore fantastic other worlds like Titan, which is
right.
All right, I'm going to take two more questions. We have Ms. Puno's class join us. I don't know how much they got a chance to see, but we're going to go to them. And if you guys have a question about Titan. Hi, guys. Now, I know you guys came in quite late. Do you have any questions about Saturn or Titan or space or research?
We just had a space presentation yesterday, and my students we're a first grade class.
Yeah.
And they do have questions. Fareed, you want to go up there and read your question, Fareed? Okay.
How hot is the sun?
How hot is the sun? Totally. There you go. Thank you so much. Great question.
That is a good question. So the sun is, and I don't study the sun, but I'm lucky enough that I kind of know the answer to your question. So the sun is about 6,500 Kelvin, which is really, really hot. It's so hot that if I told you what that was in Fahrenheit or Celsius, it wouldn't actually mean anything. So I would highly recommend not touching it, because you would definitely get burned. But it's pretty hot. It's much, much hotter than the places that I study, which are very, very cold. They're much colder than the coldest places on Earth.
Very cool that wherever you go in the solar system, there's this huge diversity of landscapes, places, temperatures, chemistry, and very neat stuff. So we've been doing sessions all month. So if you guys want to check out things on Europa, on Mars, on Jupiter, we've had sessions this month that have covered those, and it's a really fantastic diversity. Thanks for the question, guys. We're going to wrap up with another question from Miss Coyle's class, because every time we go there, they got a bunch of hands up. So Miss Coyle, if you guys want to wrap us up, go for it.
Why do you call it Titan?
I actually don't, and at some point I knew the history of how it got named Titan. So the names in the solar system are all named are like mythological.
Yep.
At least for the planets, and a lot of the moons that we first discovered. And Titan is actually kind of a weird case, because the Titans are a class of mythological creatures, not just one specific creature. And so it's kind of weird because a bunch of Saturn's other moons are named after Titans, the creatures.
Yeah.
And so it's kind of weird that they ended up doing that. It's very fitting though, because the Titans, the idea is that they're very large. And so Titan is the largest moon of Saturn. So I guess it makes sense that way, but I forget exactly how it got named. At one point they were all just numbered, which is weird. And you still see that in some of the very, very old papers where they're being referred to by their number and not their name.
But I'm really glad we got that brought up. It actually hasn't been brought up in any of our presentations that all the planets are gods. We've got Mercury, we've got Mars, god of war, messenger god, we've got Jupiter, king of the gods. So it's really, really interesting history. And I encourage you guys to check it out. And I'll see if I can find something to pass to the classes when we're done. Sarah, before we wrap up, is there any last message you want to share with classes about how they can learn more about Titan, learn more about space, the work that you're doing and beyond?
Yeah, that's a great question. With this huge range of ages, it's a little hard to suggest anything specific. But there's a couple of really great books about Titan, although most of them are probably more like high school level or older, that were written by someone named Ralph Lorenz, who is actually the project scientist, so our like kind of head scientist on Dragonfly. There's also a really cool documentary on Netflix about Cassini. So I think if you just were to search Cassini on Netflix, you would actually find more than one. But there's a couple of ones that are pretty neat that you could learn some stuff about. But I also just think that actually my favorite place to learn stuff is if you go to the Planetary Society blog. They have all different planetary scientists and then people who work at the Planetary Society write articles about all different kinds of things. So they write really detailed articles about how, like, I'm just making this up, but there probably is one, like how the arm on Mars Curiosity works, or like how storms work on Neptune or whatever. And so there's just so many different articles there that you could read about that are really great. And those are going to be like a different range of how technical they are depending on who wrote them. So there might be some stuff that would be appropriate for our younger guests today.
Marvelous. Well, I'll share that with classes when we're done. And so, Sarah, thank you so much for joining us. At the end of every presentation, what we do, I'm going to demute everyone's microphone. So, ladies and gentlemen, boys and girls, if you guys could just join me in saying a huge thank you to Sarah for joining us today from home with the puppy, which we never got to see, by the way.
Oh, no. Do you want to see him quickly?
But thank you guys so much. Go for it. Go right ahead. Thank you guys.
Thanks.
Thank you. All right. And have a lovely rest of your day to all our classes. We hope to have you guys back soon. And till then, have a wonderful time. And thanks for joining us for Space Month. Thanks so much, Sarah.